In this video, we will discuss how the sanity check is a very useful tool to help prevent models from problems when it is time to begin the solve. The sanity check will inspect the model to find any potential problems prior to solving the model. It can be run independently of the solver by going to Solve, Sanity Check. It will also run every time when you begin a solve. All problems found in the sanity check will be reported in the message window. There are three categories that these messages can be recorded in. The first category is errors. This means something is wrong with the model and it needs to be fixed. The solver will not continue until those issues are corrected. The second category is warnings. A warning message could mean something may be wrong with your model, but a solve is still possible. You should review all the warning messages to understand what the warning is telling you before continuing the solve. And the third category is informationals, which are items of interest but not usually indicative of a problem. Now let's look at some common messages. One common error you may see is when you have multi-fluid model and the two fluids are touching without a solid boundary in between them. If you don't have that solid boundary, then you will receive an error prior to the solve and you need to fix it to continue. A coordinate location will be given to you and you can create an object or a monitor point with those coordinates to identify the problem area. Next up, we have common warnings. The most frequent warning message you will see is that an object has been entirely overwritten. What you need to be aware of in this situation is that the last object in the project manager tree takes precedence in the event of two objects being coincident. So the object lower in the project manager tree will take precedence. In the next slide, I'll show you an example of this. Another common warning could be that object lies completely outside of the solution domain. This one usually indicates that you have made a mistake in the geometry setup or the computational domain definition. This is usually easy to identify and remedy. Third common warning is that the fluid flow is entirely blocked by solid or heat flow is entirely blocked by insulator. A couple examples of that could be a fan blowing directly into a wall, or heat is released into an object which doesn't have a material setting, so the heat has nowhere to go. Now back to the warning that the object has been entirely overwritten. Here's an example. What we have on screen is a common Flotherm setup. We have a component, thermal interface material, a heat sink, and a PCB. On the left and right hand side of the screen we have two ways we could model this in Flotherm. Only one will give the desired effect. On the left we have the compact component on the top, followed by the thermal interface material, then the heat sink, then the PCB. This case will have a conflict. The thermal interface material and the heatsink surface share a space. Because Flotherm solves from top to bottom, the object that is lowest in the tree will take precedence. In this case, the thermal interface material will be completely overwritten by the heatsink. The correct way to model this situation is shown here. Here, the thermal interface material is below the heatsink, and in that case, it will take precedence.